Hello, can you hear me? Yep. Yeah, so I'm very grateful to be invited here to give this talk. I'll be talking about sort of how data plays a strong role in training a lot of our AI and machine learning models, specifically large language models. And next slide. Yeah, so my title of my talk is basically Fueling Intelligent AI, How Data Drives Large Language Model Training. Next slide, please. Yeah, so I'm a third-year computer science PhD student at Stanford. Previously, also studied at Carnegie Mellon and the University of Waterloo in Canada. So generally, my research interests hover around natural language processing, so machine learning for language. I've also done some work with computer vision, multimodal grounding, and more recently, interdisciplinary work with cognitive science and psychology as well. I also run the Stanford CS25 Transformers course, which will be running again starting this April. So if any of you guys are interested, feel free to check it out. Next slide. Yeah, so basically, the sort of focus of my talk is on data itself, which, as I'm sure a lot of you know, is sort of the fundamental fuel of our AI and machine learning models, and arguably the sort of most important aspect of machine learning training. This is especially the case when you're training very large models like large language models, which require large amounts of data in order to effectively learn the sort of real-world distribution of language. Because of its importance, it's very important that we're able to maximally leverage sort of the data and get the most out of it. So what makes sort of high octane fuel or data for our language model training? Next slide. Yeah, so this sort of question that I seek to answer with two of the recent projects I've worked on is how can we train language models more effectively with smart data strategies? So I'll be sort of summarizing two recent projects. One is a work at Stanford looking at can we train small models on small amounts of data, specifically childlike data or the data that human children are exposed to while growing up. And the second looks at much larger scales. So training large models on trillions of tokens using this sort of formalized two-phase training approach with optimal data blending per phase. Next slide. So there's some central themes across these projects. The first is sort of looking at data efficiency versus volume. So you do certainly need a certain quantity of data in order to train your models effectively. But we find that, you know, if you're smart about it, you can sort of get more out of smaller amounts of data. Also, it's very important that you're not only looking at what's the data you're using and how much of it, but actually choosing the correct data at each point in time of training and ordering it in effective ways. For example, using curriculum-based approaches is very effective. Furthermore, it's not simply about throwing together random data from the internet, as I'm sure a lot of people think LLM training is about. But it's important to basically refine the data mixtures or blends, so optimally combining data from different sources. And these sort of smart training strategies using data effectively leads to the ability to more generalize to different sort of downstream tasks and makes your models more robust. So there's a lot of advantages to this. Next slide. So basically, I want to first touch upon, you know, like, so how do humans learn differently from neural networks or something like ChatGPT? This is sort of analogous to examining how the human brain might learn, for example, differently from a neural network that uses back propagation. Next slide. So some key differences are potentially, firstly, that we as humans learn continually. For example, I'm still learning right now from giving this talk, talking to you. I'm absorbing information from the world and learning continuously versus a large language model, a machine learning model, which you typically train through with a single pass, for example. Further, our learning and sort of the way we approach everything in the world is more interactive and goal-based versus a lot of our LLMs, which are basically autoregressive or predicting the next token given all the previous tokens. We also learn and reason in a grounded or multimodal fashion. So we're continuously, again, absorbing information from the world, things we can see, feel, and touch. And this guides our behavior and learning compared to these models, which are typically text-only or simply something like text and image. And further, I think our brains fundamentally learn differently from these models. So again, these models are learning using autoregression or statistics, whereas I believe we are doing more high-level things, for example, hierarchical or compositional-based learning. And the focus here in my talk is specifically on potential language data differences between how models and humans learn. Next slide. So basically, as a child, on average, from the ages of 0 when we're born to 13, so a preteen, we're exposed to approximately 100 million words of language data in total. This is typically things like children's stories books, as well as dialogue and feedback. So dialogue between the child and other children, their parents, babysitters, and so forth. Next slide. Whereas these machine learning models, especially LLMs, are typically trained on trillions of tokens. So this is 5 to 6 magnitudes or more tokens compared to humans. And it's typically more noisy data throughout the whole internet, things like Wikipedia, books, and so forth. So why do we care about sort of small models and small data? Well, this might lead to a lot of advantages. The first is, of course, greatly improving the efficiency of training and using our large language models. It may open up new doors and potential use cases like minified LLMs that you can run or train locally on things like your phone, as well as the fact that small models in general are more interpretable and easier to align compared to huge LLMs, which are more black box models. And lastly, investigating more about how sort of we can get our models to learn more efficiently might even shed insights into the psychology or cognitive science side of things. So how come we're able to learn language so efficiently, and how we can bridge that gap between LLMs and humans? So the first sort of project I'll be discussing briefly is this one titled, Is Child-Directed Speech Effective Training Data for Language Models? So I presented this in Miami at EMNLP in November, and this is a work with my Stanford professors, Noah Goodman and Michael Frank. Next slide. So as I stated earlier, human children are much more efficient learners. We can learn on several magnitudes less language data than language models. Now, a key question here is, why is this the case? Is it because of the data that the children are actually exposed to, or the actual learning algorithm in their brain? And one possibility is that the data that children receive is naturally curricularized to support learning. So basically, no, next slide. Yep. So 2 research questions we directly answer is, can child-directed speech serve as effective training data for language models? So this means that the actual speech that children are exposed to. So these are conversations, textual conversations between children and other people, for example, their babysitters, teachers, and so forth. And the second is, does global developmental ordering affect language model learning? So what this means is, if you order the training examples based on age, for example, age 0 to 13, in a curricularized fashion, similar to how a children learns, does that lead to better learning compared to randomly shuffling everything, which is typically how machine learning models are trained? So we train some smaller models, GPT-2 and Roberta, which are 2 different models, an autoregressive left to right LLM, and a mass language model, on 5 different data sets. So one is ChildS, which is natural conversations with children. This is transcribed to text, of course. We collect our own synthetic version of this called Tiny Dialogues. Baby LM, which is a heterogeneous mixture of text from different domains, including Wikipedia and so forth. Wikipedia text, of course, and open subtitles, which are movie and TV transcriptions. Next slide. So the sort of motivation for training on child-directed speech or collecting tiny dialogues is that, again, a large portion of a child's language as they're growing up, language exposure is through conversations with other people, right? And conversations naturally lead to learning. When we talk to people, we get things like feedback from them, and we can even, it also leads to more self-reflection. And this is not learning of just knowledge, but even things like values, ethics, and morals, so things like alignment. Because parents and teachers, for example, tell us what's right or wrong, and that's a very important thing while growing up. And many different types of conversations happen with different people, so there's a variety of content and learning possibilities. And I might speed up a bit, but yeah, next slide. So we collect approximately 130,000 child-directed conversations using GPT-4 with a restricted childlike vocabulary. Next slide. And these are some examples. So you can see that the participants' content and the complexity of the language and the length of the conversation differs depending on age. Next slide. We also test, again, some ordering effects. So again, global order or child age, so ordering conversations from younger age to older, reverse or random shuffling. And we also try shuffling utterances within conversations to test local ordering effects. Next slide. We test two fundamental capabilities, so grammatical knowledge using Zorro, as well as semantic knowledge or word similarity. Yep. So here are some results. So you'll see here that actually training on a heterogeneous mixture of random internet text using baby LLM leads to better results on both metrics on compared to our child-directed speech. And you also see that our tiny dialogues dataset leads to better performance, specifically on word similarity learning. Next slide. And for global ordering results, you'll see surprisingly there are not many differences between ordering examples by age, reverse, or random. So we kind of looked at why is this the case by examining convergence behavior. And you'll see the blue line is training loss. You'll see this actually differs locally depending on what order you use. However, the overall learning behavior, especially generalization through validation loss, has the same trend no matter what. So this kind of shows that it doesn't really matter how exactly you curricularize or order your data. Next slide. So again, diverse data sources seem to provide better learning than purely child-directed speech. Synthetic child-directed speech seems better than natural. And global developmental ordering or curriculum learning seems to have minimal impact. So basically, our conclusion potentially is that other aspects of children's learning, not simply the data, are likely responsible for their efficient language learning. And the child's learning algorithm may simply be substantially more data efficient than current language modeling techniques. So it's less about the data difference and more, for example, other things. And please feel free to get in touch or check out our GitHub repo, which has our code and data. Data has been uploaded to Hugging Face, and our paper for more details. Yep. Next slide. So now let's scale up much bigger. So now I'll be talking about my second project, which is called Maximize Your Data's Potential, Enhancing LLM Accuracy with Two-Phase Pre-Training. And this is a work I did with NVIDIA last summer during my internship. So LLMs, of course, rely on extensive data from very diverse sources, such as the internet. Data blending and ordering are crucial, but they're sort of underexplored aspects of LLM pre-training. And many existing works like Llama highlight this sort of importance of optimizing your data mixtures, but they're not very transparent about their details and experiments. So we want to answer what exactly works and why or how it works. Next slide. So some key contributions of our work is that we formally define and systematically evaluate this thing we call two-phase pre-training. We validate that it works better over continuous single-phase pre-training. And we do a sort of fine-grained analysis of data blending for both pre-training phases. And we also find that we're able to prototype blends on a smaller token count and then scale up effectively. Next slide. Yep, so our two-phase pre-training approach is basically separating the pre-training process into two major phases. The first is training on a more diverse data mix to build a broader base of language understanding, and then later shifting to a more higher quality domain-specific data for refined performance. And you'll see an example at the bottom where our phase one is a lot more dominated by web crawl and general internet data, whereas our phase two has a lot more specialized data like math and code. Next slide. We have various data sources, web crawl, high quality data like math and code, medium quality data like books, patents, and papers, and as well as some multilingual and task data such as FLAN. And we evaluate several fundamental capabilities across things like reasoning, general knowledge and understanding using MMLU, mathematics, as well as programming. And our model setup is a 7 billion parameter Megatron model, which is also an autoregressive LLM. And we also have a scaling experiment to 25 billion parameters. And we also prototype our blends with 1 trillion tokens, and also show the results on the full 15 trillion tokens. Next slide. So does phase two training actually help? So does breaking the training down into two phases help? And we sort of switched to phase two after approximately 700 billion tokens. And yes, all phase two blends outperform the baseline of continuing phase one training all the way to the end. And our two-phase approach is better than, for example, randomly ordering all of the data by sort of blending both phases of data mixtures and training continuously in a single phase. So yes, our two-phase sort of approach is substantially better. Next slide. And furthermore, this approach is scalable. So scaling up to higher token counts and model sizes leads to better performance across the board. However, you require balancing quality and number of epochs of data sets. So it's important that when you scale up, you not simply still take the same absolute number of tokens, but you actually make sure to reduce the absolute number of tokens per high quality data set to make sure that the number of epochs exposed is still similar, because this prevents overfitting or overexposure on certain data sets. And this highlights the effectiveness of prototyping data blends on downsample number of tokens and then scaling up. Next slide. And we also investigate the impact of the phase 2 duration, experimenting from 0% up to 50% or half of pre-training. And we found that performance scaled better up to around 30 to 40% and then decreased across the board. And this is also likely due to sort of overexposure or overfitting when you're exposed to too much high quality data. So overall, we find that well-structured two-phase pre-training for large language models with careful data selection and management is essential for optimizing LLM performance while maintaining scalability and robustness across downstream tasks. Next slide. I think there's an issue with the right, so feel free again to check out our paper, get in touch. There's a lot more details on the paper there. Next slide. Yeah, so some general thoughts just to tie things together since I'm out of time. Next slide. So data effectiveness, as we see, is not just volume, but it's looking at things like quality, ordering, and structuring of the data. For example, from our first project, we found a negligible impact of global order and small-scale data, but we found an impact of this sort of two-phased data mixing approach for large-scale training. And again, smart data decisions are essential to train LLMs that can generalize across many different downstream tasks. So one final thought is that basically our research sort of underscores that effective language modeling isn't just about amassing large amounts of data, but about smarter data organization that effectively harnesses its structure, quality, and characteristics. And by continuing to sort of refine data-centric approaches, the future of LLM and AI training in general promises smarter, more efficient, and highly adaptable models. And that's my talk. So feel free to get in touch if you have any questions and to check out our papers. Thank you.